Okay, so thank you very much. So yesterday I presented a general modeling approach for breaking and non-breaking waves. The objective was to be able to describe wave propagation from the shoaling zone to the swash zone. We use a very pragmatic approach, which is the following. So for non-breaking wave, we use Serre-Grignaldi equations. And for wave breaking, we shift to the Saint-Venant equations at the level of broken wave fronts. So remember, there are also some physical criteria for determining the onset of wave breaking and the cessation of breaking. And I presented some validation for periodic waves, and also for this case of wave propagating over a bar. In that case, there are a shoaling effect, wave breaking over the bar, and due to the increase of water depth and the decrease of nonlinearities, the harmonic generated in the shoaling zone and in the surf zone becomes free and propagate at their own celerity given by the linear theory, the linear celerity. So you can observe such a secondary wave, short wave, and the model gives a relatively good agreement, even for the cessation of breaking and the liberation of free harmonics. So now a new validation, especially to assess the ability of the model to reproduce the shoreline motion, and especially the multiple shorelines case. So you can see here a solitary wave propagating over this beach and reaching a seawall. So there is a first shoreline here, but after breaking, you will see other shoreline behind the seawall. In this experiment, there are several probes, several elevation gauges. Just here, one, and in the shoaling zone, in the breaking zone, and just behind the seawall. So you can see here the first probe. In blue, it is the Serre-Grignaldi model, and in black, the laboratory experiment. So you can see that at the beginning of the decreasing water depth, that the solitary wave is already well reproduced. It is the evolution, they represent time series. Sorry. And you can see here another wave train, which is related to the reflection of part of this wave on the seawall. So this component corresponds to a reflected wave propagating in this direction. And this part of the wave is close to an ondular bore, an ondular dispersive bore. And once again, it's relatively well reproduced by the model. Then in probe 28 here, at the beginning of the swash zone, you can see an increase of zeta, a strong increase, which is named the run-up, and then the run-down at the seawall level. But of course, part of the wave overtops the seawall, and you can see in probes 37 and 40, just behind the seawall, that we are able to reproduce the beginning of the overtopping, but with some with a less accurate simulation, a less accurate agreement behind the seawall. So globally, relatively interesting result, agreement with numeric with experiments, and the model is able to deal with multiple shorelines. So it's an academic case to validate the model, but of course we want to use such approach for real applications, especially during storms. It's just a comparison. Whoop, it just I forgot this slide. It's just a comparison between a depth average model based on Serre-Grimaldi equations and a much more complex model based on a 2D VOF model solving the Ron's equation, Reynolds average Navier-Stokes equation, with a parametrization of a modeling of turbulence with a K-epsilon model. So it is a much more complex model. And globally, we observe nearly the same accuracy in comparison with a laboratory experiment, except behind the seawall, where this complex model gives slightly better results. So our objective, of course, is to apply such approach to real situation and to evaluate the impact of storm in a situation of flooding for city or other region. So now I will present you a simulation of flooding during the Jonah storm hitting Brittany in 2008. These simulations were performed by the BRGM, which is the French organization for coastal hazards. And they use a SURFWB code developed by Fabien Marche. So you can see the French coastline, the field site, and the generation of wave at the beginning of the storm. So you can see wave propagating. It is a fast motion video, of course. You can see the evolution of time, so it's really a fast motion video. And sometimes you can see overtopping, mainly related not to each wave, but to infragravity waves. Sometimes there is a pulsating motion and flooding of some streets, here. So the wave height is increasing during the storm, and you can observe flooding, strong flooding over meadows, and progressively flooding of the whole city. Very strong, very strong flooding, strong overtopping, and a progressive flooding of the whole area. And this simulation is in qualitative, not really quantitative, but it is in relative agreement with these events in 2008. So now I will discuss about the mechanism of wave-induced currents. So perhaps you remember at the beginning of the course, I presented some typical, the most important rip currents generated by wind-generated waves. Rip currents, which are narrow, seaward-oriented currents associated with vortices, macro vortices. And remember that these currents are the main cause of drowning on the beaches. and also the longshore current, which is a current parallel to the coast, and which is generated when the wave propagates obliquely to the coast, and due to wave breaking, there is a transfer of momentum from the wave field to a mean current parallel to the coast. So this current is very important in the context of morphological evolution, because these currents induce strong sediment transport along the beach. So to understand the physical processes which are associated with this mean current circulation, we have to do a decomposition between wave and currents. Waves including wind-generated waves, short waves, and also infragravity wave. So we consider that there is a characteristic time scale, capital T, which separates waves from mean currents. And then we can define the wave field, a tilde, and zeta tilde for the velocity field and the elevation field, as the flow field, capital U, minus the time average of this velocity. And the same thing for elevation. So we decompose the velocity in terms of a mean current and a fluctuation velocity related to waves, short waves and long waves. And U bar, zeta bar, represents the mean circulation, which represents a slowly varying function of time. So let us start with the mass conservation equation. We can average this equation like this, and developing this term, we get this equation where you can see here H bar, U bar, capital U bar, which is the mean mass flux, the mass flux related to the mean circulation, and this term, which is the mass flux related to wave. So if we consider a stationary wave field, a special example so the mass equation, the average mass equation, write like this: H capital U bar. So considering a stationary wave field over a long time, we can eliminate this the time evolution of the mean surface elevation, and so the mass flux associated with the mean current is equal to a constant. And at the shoreline, this mass flux is, of course, equal to 0. So this constant is 0. So that means that the total mass flux, H bar, U bar, plus the mass flux induced by a wave is equal to 0. And we know that this quantity is positive because for a wave, the surface elevation, zeta, and U, the U tilde, are in phase. So at the crest, the wave is positive in the direction of propagation and negative for minimum elevation. So this quantity is positive. So that means that there is a mass flux associated with wave in the direction of the beach. And to compensate this, to balance this mass flux, it is necessary that a mean current induce a mass flux in the opposite direction. So we can compute a mean current U bar, which is expressed in function of wave characteristic divided by h bar. So from a mass conservation equation, we can deduce that U bar is negative. So to counterbalance the mass flux related to wave, there is a mean current in the opposite direction. So there is a balance between the two processes. And this current is well known in nearshore dynamics, is named under-tow current. So first, wave-induced current. And this current plays a really significant role in sediment transport, cross-shore sediment transport. Indeed, so your sandy beach, wave shoaling, breaking, onset of breaking, and the surf zone and the swash zone. In the shoaling zone, the sediment transport is mainly related to the asymmetry, the horizontal asymmetry of orbital velocity, of wave velocity. Remember that in the shoaling zone, the waves are relatively nonlinear with a shape, so zeta, with a shape like that. So a broad trough and a relatively narrow peak extremum of elevation. So it is typical of what we observe in the shoaling zone due to nonlinearity. So there is a strong asymmetry around the horizontal axis. So it is the velocity. It's elevation, but also the velocity, the cross-shore velocity. So we can imagine that at the crest, at the wave crest, there is a flux of sediment in that direction, and in the trough in the other direction. But the sediment flux is proportional to U tile, at the power 3. It's a well-known result. So the sediment is proportional to U tile at the power 3. So the impact of the maximum velocity, positive velocity, is much more important than the sediment transport in the opposite direction for the wave trough. So you can see that there is an unbalance, and globally, the mean sediment transport due to such wave is in this direction. The net sediment transport is shoreward, okay? But in the surf zone, the process is totally different. The sediment transport is mainly controlled by the undertow. So in the surf zone, the sediment transport is in the opposite direction. So this convergence of sediment fluxes lead to an erosion and an accretion. And so the undertow can explain why we generally observe a sandbar at the beginning of, at the onset of wave breaking. So the undertow plays really a significant role for sediment transport and beach morphology evolution. Now we are dealing with the momentum equation. Without a broken wave, without shock, here you can see the non-conservative momentum equation, and we can average this equation over time, which is this, and finally this equation with a forcing term, which is related more or less to the energy of the wave field. So for a regular wave, without shock, it's straightforward, there is no problem. But in case of periodic broken waves, shock, the integral of this term, called m, is not obvious, and we have to take care of this time integration. So the derivative of the mean value of the mean of m is like this, and we consider now that there is a shock or bore, and so the time signal is like that, the elevation, the time, and so the signal is like this, a shock, continuous wave, another shock, okay? So t plus characteristic time t, or the wave period, and the location of the shock is t equal ts. So to compute this integral, we decompose it from t to ts minus and ts plus to t plus capital T. And using Leibniz rule, we can permute the derivative and the integral, and we found this expression, and the same for the other. And so Ts is the time at which the shock is located in x, so it is a function of space. So for a regular part of the wave field, we can use this continuous equation for m and replace this quantity by du dt. And finally, we obtain this equation for the mean currents, which is with a forcing term here, where this term look like to energy or a dynamic pressure related to wave. And the most important term is d, which is given by this equation, where the bracket is associated with a jump in the m quantity. And from the shock condition, we can compute the value of d, which takes this very simple form. And you can notice that it's very close to the dissipation, energy dissipation, wave dissipation in shock, and proportional to h2 minus h1 to the power 3, so proportional to the wave height to the power 3, and in fact it is proportional to the mean dissipation in broken wave. So this term is a source term of the mean momentum equation, which is related to energy dissipation. And this force is named dissipative force. And physically, this dissipative force is due to the fact that wave breaking induces a decrease of momentum flux and of the wave momentum flux, and this to apply the conservation principle, there is a transfer to a mean current. So the mean current equation momentum is forced by a term proportional to the dissipation of energy. And if we consider a stationary wave field, so we suppress the first term, you get this balance equation with hydrostatic pressure here, and the main term, this term is not negligible, but is very small in comparison with D, with the dissipative force. So you get a balance between the hydrostatic pressure force and the dissipative force. So D is positive, and then det zeta dx is a positive quantity. So in the breaking zone, there is an increase of the mean elevation. And you can see in this numerical simulation, in comparison with laboratory experiment, that in the inner surf zone, in the surf zone, there is an increase of the mean water level, which is named in our community wave setup. And the wave setup plays a very important role, especially during storm. Because remember that the dissipative force is proportional to the wave height to the power 3. So for very significant wave during storm, for sometime wave height of about 10 meters, the dissipative force is extremely high and generates a very strong setup, sometimes more than 1.5 meters. So that means that the mean level over which wave propagates is not the level at rest. Whoop, is not the level at rest here, but this level, which is maximum at the shoreline. So an increase on 1.5 meters is really significant and is favorable to flooding and to overtopping. So wave setup is a very important phenomenon. So in fact, we have derived a new system of equation for the mean currents and the mean elevation, so for the mean circulation. And you can recognize the Saint-Venant equation, not for the high-frequency wave motions, but for the mean circulation induced by wave. So the Saint-Venant equation with a forcing term, which is directly related to small-scale waves. So these terms are close, finally close to the Reynolds approach for turbulence. But contrary to the turbulence, the source term is not a dissipative one, but is a forcing term. We can extend such approach to two-dimensional flows. And so you can observe, you can see nearly the same structures with the Saint-Venant equation with forcing term related to wave and dissipative force along EK, which is the unit vector along trajectory ray, which are orthogonal to turbulent wavefront. By applying the curl to this equation, we obtain the vorticity equation, the vorticity of the mean circulation here. And it is very interesting because this, the vorticity, when the dissipation is equal to 0, so without breaking, outside the breaking zone, there is no forcing at all, and there is conservation of vorticity. But in presence of vorticity, especially if the vorticity is not, the gradient of dissipation is not collinear to the trajectory of waves, to the ray, there is a forcing term. It is the gradient of the dissipative force with the vector product of EK. So it's a very important equation to analyze wave circulation. So in most cases in the field, the wave field is not 2D, but 3D with localized wave breaking, especially wave breaking associated with sandbar. So there is a focalization of wave energy and breaking, which is more or less localized in a special zone of the nearshore zone. And so in that case, there is, so you can see the wave crest in this breaking region, and the rays like that. And so the gradient of the dissipation, so the dissipation is close to 0 here, and is maximum here. So there is a horizontal, it's not the gradient, but the horizontal, the transverse gradient there is also a normal gradient, but with a cross product or with a vector product, there is no generation of vorticities. Okay? So the transverse gradient is oriented in this direction, and so with a vector product, you generate vorticity in that sense, and in the opposite sense for here. So you have a dissipative force related to wave breaking, and so when you have a 2D wave field, there is no generation of vorticity. But if there are some localized wave breaking patch, due to the inhomogeneity of the breaking force, there is vorticity generation. And this mechanism can explain, in particular, rip currents. So you can see here the Aquitanian beach with intense rip current there. In fact, there is a sandbar here, a channel, another bar, and so on. So we can, you can see a schematic representation of this configuration. So with so waves are propagating from the top to the bottom. The shoreline is here, and you can see two sandbars. So due to wave refraction, wave intensity is higher on the bars than on the channel. So the maximum dissipation is located here and here. So the rays are like that due to refraction over the bathymetry. And then the dissipation is oriented like this. So this induces a circulation like that, and in the opposite direction for the other bar. And so this mechanism of vorticity generation can explain the rip current. In fact, you have a dissipative force related, which exerts in the direction of the beach, which exerts a strong strength on the water, and due to the heterogeneity of this dissipative force, there is the generation of a strong and narrow current seaward oriented. So you can explain relatively easily the generation of rip current. Are there any questions? Oui, yes?
So in the simulation here by Castel, the mechanism that you explained, based on shock wave theory, is automatically implemented in shallow water codes if they are based on shock theory also. So you don't have to add any mechanism, it's automatic. Is that it?
Yes, it's true. Okay. Yes, it's right. Yes. My presentation is to understand the physical mechanism, but it's true that with Serginaldi, with shock capturing method for the broken wave, all processes are included in the model. So with time-resolving wave model, as David explained, you can simulate such a rip current. But if you, I remember a question the first day about long-term evolution. If you need to simulate morphological evolution over a very long period, you need another approaches because Boussinesq or Serginaldi models are too much time-consuming, and so for long-term application over several months or years, to analyze, to simulate beach morphology evolution, you need to decompose mean currents and wave with a different approach. So I can present you some laboratory experiment performed in a wave flume, very large wave flume, 30 meters by 30 meters, and with wave generators here, and wave are propagating in this direction, and it is the bottom is a sandy bottom, and so you can see the wavefront propagating shoreward, and the beach morphology with a bar here and a channel here, bar and trough in the beach morphology. So due to wave breaking, the dissipative force is relatively intense here and less intense in the trough. So we have put a lot of drifters during the experiment. So it's a fast motion video, of course, because the trajectory is very slow in comparison with wave propagation. So you have a wave propagation like this, very fast, because, and you can see here the slow current motion, rip current, induced by the wave. So you can see that we can recognize the first circulation in that direction and also in the other side. But you can see that this mean circulation is not stationary. There are instationary hydrodynamic instability, shear instability, and other instability processes. And sometimes you can see that drifters are ejected from offshore, and it is exactly the same in the field. In the field, 10 or 15 years ago, when I started to study this process, we use human drifter in the field, human drifters with a GPS, so swimmers, PhD or master students. And we follow the trajectories and sometimes the expulsion of the swimmers. And, but it is not a robust method, and we prefer now other drifters, especially during storm. So you can see the time average circulation in accordance with I explained previously. To come back to the question of David, you can see, I will show you a simulation with Sergei-Nadi model of this experiment. So you will see here the surface wave elevation. Once again, it is a fast motion video, and the circulation induced by the wave. No, it's not the correct one. So you can see the propagation of waves, the wave elevation, and associated to the wave propagation, you can see the generation of positive vorticity and negative one, and also some fluctuation, pulsation of this circulation in agreement with what we observe in the laboratory experiment. We also need to take into account the effect of the tidal motion. So in the field, rip currents are of course mainly generated by the wave, short wave breaking, but these rip currents are modulated by the tidal evolution. For instance, on the Aquitainian coast, the rip currents are more intense at the mid-tide, rising tide and falling tide. So such currents are not related to tidal currents, but the intensity of the rip currents is related to the tide elevation. And the most efficient processes to induce rip current in our environment in the Aquitainian coast is reached during mid-tide. So we have to deal with also with the evolution of the tide. So we have we also carried out laboratory experiment, always in the Aquitainian coast. And you can see our field site, and you can observe a lot of rip current system. In French, in this region, these systems are named baïnes, and baïnes are really dangerous for swimmers, except for PhD and master students. And you can see the field site, and we deploy instruments in this area. So you can see a deployment of current meters, pressure sensor, a lot of many instruments. And we have observed very strong and narrow rip currents, relatively in agreement with what we observe in the field. And we have confirmed the hypothesis of vorticity generation by the curl of the cross product between the gradient of the dissipative force and the direction of wave rays. Now I would like to present you briefly the last experiment on a rip current carried out in Anglet, so in the Basque Country, a few months ago. So this we shows that this site, due to the presence of this headland, you can see here. So the beach is like this, and there is an headland, a cape, and also a reef, a rocky reef. So we know that this rocky reef will focus the wave field and generate rip current with the same mechanism I explained previously. But in this field experiment, our objective was to take into account geological constraints, such as this cape. Just a short break with a short movie, unfortunately in French, where we present the field experiment. Ouais, okay. I have a problem. Sorry. I need the. So you can see the field site with wave propagating, with the headland. So it's not interesting, and so and so you can see the circulation of wave-induced circuit. So you can see this patch of the wave breaking over the reef. And so we want to analyze the vorticity generated by the reef. So for that, we deployed current meters like this one. So we deploy current meters like this one and this one at fixed location on the sea bottom. And so we have measurements of the vertical profile, but we use also another technique based on video and drone. So we have two systems of video, one on the lighthouse and one with a drone. And so we use the video with the drone to follow the wave field. We can compute the celerity, the wavelengths, and especially from the drone, we can compute the slow motion of the foam induced by the mean circulation at the sea surface. But we use also drifter, so not human drifter, but the new generation. This part is in English, but we have no sound. No. So we use this specific. Drifter is well known in the oceanographic domain, but for large-scale trajectories. But in the surf zone, we need to deploy very specific drifters because we don't want that the drifters surf. Because we are not interested in the wave motion, but only interested in mean wave circulation.
So we have a shallow rock where we're deploying them and we're looking to track the currents that are moving around.
Okay, so they are
As well as the currents around the rock.
deploying the drifters, many drifters, and we follow with the GPS in real time the circulation and to be able to validate or not our numerical approaches. So it's a funny work. So we are now analyzing all the other database. Especially we are analyzing intense rip current along the headland, which are generated by the wave. And now we are trying to develop numerical simulation in order to compute this complex wave field and wave-induced circulation. And the best part of the movie is a cartoon at the end of the movie. It is in French. So rip currents are more dangerous than sharks. Oh, help! A rip current. The last Spielberg movie is very bad. I think it's funny. So after this short break, so you can see the field side, the current meter deployed in several locations, and the drifters, and so we combining video system to see the evolution of the form related to wave breaking. You can see the trajectories and the velocity given by the current meters. In this specific case, the wave is coming from northwest and like this, and it uses a strong current, mean current along the headland. So there is different configuration. The rip current and the circulation is very sensitive to the orientation of the wave and also, of course, of the intensity. And a slight variation of the wave direction strongly affects the dynamics. So it's a very complicated problem. And so it is why now we would like to perform some numerical simulation in order to understand the sensibility to wave condition, wave orientation, and wave intensity, but especially wave orientation. Are there any questions? No? Because now we will jump to a totally different process. We are discussing about, we are going to discuss about long waves, such as tsunami and tidal bores. So the generation mechanism is totally different, of course. Previously, the waves were generated by winds. And in that case, for tsunami, strong, intense tsunamis are more generally generated by earthquakes, a strong motion of the the Earth, generating large amplitude and large wavelengths, long waves, and also tidal bores induced by tidal motion. So you can see two nice photographs of ondular bore propagating shoreward, associated with a tsunami and a tidal bore. So you can see that there are many similarities between bore induced by tsunami and by tide. So now we will analyze long wave dynamics. So long wave, for instance, tsunamis, tide, but also infragravity wave, and there are other phenomena related to other long wave phenomena. So you can see here the evolution of a tsunami, a schematic one, with a characteristic length of 50 kilometers and a characteristic amplitude of 2 meters. In blue, it is a Sergin-Nadi simulation, and the dashed line corresponds to Saint-Venant simulation. So at the beginning of the propagation, you can see that there is no difference between Sergin-Nadi and Saint-Venant approaches. It seems quite obvious because such a long wave are associated to very, very small mu parameter. So the non-hydrostatic terms at the beginning of propagation, especially in deep water, is a process which is mainly non-hydrostatic. So for tide, and in that case for tsunami, the Saint-Venant does a very good job, and we don't need a dispersive and non-hydrostatic process. But as the wave propagates, due to nonlinear effects, the wave becomes more and more steep, and you can see here the appearance with the Sergin-Nadi equation to an oscillation. It is not a numerical oscillation, but it is a dispersive, physical oscillation related to the effect of dispersive effect. And as the tsunami propagates, the nonlinearities are increasing, and the non-hydrostatic processes too, with a very strong ondular bore behind at the wave front of the tsunami. So this bore is a non-breaking bore. It's just an oscillating bore, which can relatively well described by approaches such as Sergin-Nadi model. And when these oscillating waves are reaching a slope, a bed slope, the amplification of the wave becomes very significant, and the first wave starts to break, and after the second one. So it's typical of what we can observe during some tsunamis at the nearshore level. So there is a bore formation or long wave breaking. And you can see on these photos an example of the wave field associated to the Sumatra 2004 tsunami reaching the coast of Thailand. So you can see nice bore, ondular but also breaking bores, propagating shoreward and breaking another time at in shallow waters. You can observe nearly the same process for infragravity waves. So the characteristic timescale and space scale are totally different, of course. This is not 100 kilometers, but the characteristic scale for infragravity wave is 100 meters, and the characteristic time scale is about 1 to 2 minutes. And when such an infragravity wave propagates into a beach channel, you can observe such ondular bore propagated in this channel. And now another nice video of this process. Je suis désolé, la musique, mais bon. So you can see the tidal bore in the Gironde estuary, close to Bordeaux. It's very intense phenomenon. You can see the ondular bore, a lot of surfers, many surfers. Oh, where is stuff? So it's very spectacular phenomenon with intense secondary waves. So it's occur at the beginning of the rising tide. You can see that the river is relatively large, and the bore is along the whole cross-shore section of the river. So we analyze this process in the Gironde estuary, and more specifically in the Garonne estuary. So you can see this estuary, and we deploy several gauges, tide gauges, at the entrance of the estuary in blue. So you can see that the tide is not sinusoidal, but relatively close to a sinusoidal one. And as the wave propagates in the estuary, the wave becomes more and more nonlinear and more asymmetric. So in the mid-estuary at Pauillac in red, you can see that the beginning, at the end of falling tide and beginning of the rising tide, the flow is very asymmetric. In the deep ocean, there is a relatively continuous evolution at low tide, but it's not the case after, due to the strong nonlinearities of the tide. And then in Bordeaux, about 90 kilometers from the sea, so it's very far from the sea, you can see in blue that the asymmetry is very strong. And also you can observe an amplification of the wave. And the maximum of the tidal range, so the wave height, the tidal height, is not at the entrance of the estuary, but 120 kilometers up the estuary. So it's a really impressive phenomenon with a strong amplification of the tidal wave along the estuary. And if we zoom the beginning of the rising tide at Bordeaux, you can observe a small jump, a very small jump, relatively smooth. The jump occurs over a period of about 100 seconds, several minutes. So it's a relatively smooth jump. And as the nonlinearity increases and the asymmetry, you can observe at Ponensac, is not numerical oscillation, but field measurements. You can observe very strong tidal bore. And you can see here a photo related to this measurement. So you can see the structure of the tidal bore. So there are an intense ondular bore generated 120 kilometers far from the ocean. So such tsunami-like bores related to tsunami, to infragravity wave, and to tidal bore have a significant impact on ecosystem. For instance, tidal bore, for tidal bore, they have very strong acceleration for the velocity. At the rising tide, the velocity is about 1 meter per second. And in 1 or 2 seconds, there is a reverse of the current and a velocity of 1.5. So from -1 to 1.5 meters. And so the acceleration is very, very important. So with a strong impact on sediment transport. We have deployed pressure sensors with a system of about 100 kilograms, and they were like a drifter in this environment. They were not stable, even with very heavy structures. So the sediment transport is very significant. There are also impact on for tsunami on marine structure and building. Of course, you remember the last tsunamis in Sumatra and in Japan, with a lot of damages. To study and to evaluate, to assess hazard related to tsunami, an experimental, a lab experiment was carried out in the States. It was a laboratory in similitude with the seaside coastline, the seaside city in Oregon, USA. So you can see in a very big waveframe, they reproduce the city with all buildings and streets and so on. And they generate a tsunami in the waveframe. So we use these laboratory experiments to assess the ability of an operational model, WINA, that we are developing at Bordeaux. It is a collaboration between IMB with David Lann, INRIA with Mario Ricciotto, my laboratory, and also IMAG in Montpellier with Fabien Marche. So we would like to develop an operational model for wind-generated waves, but also for tsunami and tidal bores. And the ability to well represent the shoreline motion and the overtopping is very important for such application, and to assess the coastal hazard. Sorry, it's also a video. Je ne suis pas dans le bon sens. So you can see the tsunami breaking and impacting the city. So there are some reflection here and here because we are in a wave flume, so with a boundary at here and with lateral boundary condition. So the model is able to reproduce the evolution of the wave, the breaking, and the strong impact of the wave, of the tsunami, with buildings. And we compare and with probe data, and there are relatively good agreement between model and field laboratory observation. So what? I have 20 minutes? Okay. So the question now is, what are the conditions for the generation of bore in coastal and estuarine environments? So I jump this part. So to study this phenomenon, we use a shallow water approximation. So you can see here the Green-Naldi equation. And you remember that, in fact, the shallow water equation is able to reproduce the wavefront propagation, but without, of course, the dispersive effect. So to analyze the onset of the appearance of Bohr, we don't need to take into account dispersive effect. Of course, after Bohr generation, dispersive effects are very important. But for the initiation of wave breaking, we don't need such a dispersive and non-static process. So to analyze this process, we will use the classical Saint-Venant equations. So there is epsilon 0, which is a nonlinear parameter, and there is also another one, S0, which it is a dimensional parameter related to the beach slope. So now there is a schematic sketch of continental shelf. So you are the deep ocean with water depth of about typically 4,000 meters, 4 kilometers, a tsunami or a tide propagating, and there is a jump which is named a Continental Shelf, and it is relatively flat here, and with a characteristic water depth of about 150 meters. And there is a characteristic length scale, LW, for the tsunami or the tide. And the question is, where is the Bohr inception? We would like to know where the Bohr occurs. And for that, so we neglect the bathymetry variation over the continental shelf. And you remember that point. We are able to compute the location of the onset of breaking, which depends on the characteristic length scale of the tsunami and the nonlinearity parameter. We derived this expression yesterday. So it's just an approximation, but it's just an order of magnitude. But we can evaluate the position, the occurrence, the onset of Bohr formation. Of course, XS should be smaller, of course, than the length of the continental shelf. It's obvious. So, continental shelf, you can observe a water depth of about 150 meters. Considering tsunami, the characteristic amplitude for intense tsunami is about 2 meters. The characteristic time scale is it's just an order of magnitude, about 25 minutes. So if you apply this equation, you find XS equals about 460 kilometers, which represents a distance which is much larger than the larger continental shelf. So the conclusion is that there is no tsunami Bohr in open sea. You will see that it's not so simple. And for tides, the characteristic time is about 12 hours, 2 tidal cycles per day. And the excess position is much, much larger than the continental shelf width. So no tidal Bohr in open sea. But, in fact, close to the nearshore zone, sometimes you can observe flat environment and relatively shallow, such deltas, alluvial estuaries, and carbonate platform, for instance, coral reef system. In such nearshore environment, the water depth is very small, not 150 meters, but about 10 meters. And all it changes with such a shallow water environment. And so, using this expression, we can compute excess, and in that case, tsunami bore can occur. So tsunami bores occur in very shallow nearshore environments, shallow and long, because the bore formation needs time and distance. So most of the time, tsunamis over the world tsunamis don't generate underwater bore. It occurs only in very specific shallow environments, such as coral reef system, for instance. And tidal bores never occur in open sea, but can occur, of course, I've previously shown, in estuaries, because they are very long, and so in agreement with this criterion, and sometimes very, very shallow with a characteristic water depth of about 10 meters. However, in our approach, we have neglected the friction, because in deep water, it is a good approximation. But in such a very shallow environments, the friction can play a very significant role. So we have to include friction in our process. Okay, it's just now I jump to another time to tidal bore. We can observe tidal bore all over the world. For instance, a famous one is bore is propagate on the Severn River in England, the Pororoca in the Amazon River, the Kampar River with the Bono tidal bore, and the most intense tidal bore is in China on the Guangtang River. Hop, hop. So, sorry, there's no time, I think. Hop. So now we come back to the equations. These equations represent the integration of the flow motion in shallow water integrated across the river section. So it is a 1D model, but this model takes into account the variation of the area section of the river. This quantity is negative in a funnel-shaped estuary because the section is reducing upward. And we have added this term, a quadratic friction terms. And remember the evolution, the nonlinear evolution of tide. The asymmetry was totally different than the asymmetry for tsunami. It was a little bit special because the singularity doesn't occur at the top of the tidal wave, but at the trough. And the asymmetry was a little bit curious. It is because in this equation, in this phenomena, the leading nonlinear terms is not the advective one, but the friction one. So it's a funny processes, I think also for mathematicians. The nonlinearity is dominated by the quadratic friction terms and not by the advective one. There's no time to describe. So we have, from that, we were able to perform dimensionless analysis, and we have identified two main dimensionless parameters. The first one is epsilon, which is a nonlinearity parameter. So the characteristic tidal amplitude divided by the characteristic water depth. Okay. So we can imagine that for large epsilon, we observe large tidal bore. It seems quite obvious. But we have identified another dimensional parameter, which is related to friction effects. And we were able to classify all estuaries over the world, all convergent and shallow estuaries over the world. You can see some of them. In black, a convergent estuary and shallow estuary where there is no tidal bore. And in red, estuaries where we can observe tidal bore. And you can see that there is a critical curve, epsilon c, which is function of phi 0. For a given friction, a dimensional friction parameter, the process is related to epsilon 0. When epsilon 0 is greater than the critical value, bore occurs. And below there is no bore. We have compared. It is a relatively qualitative observation from about 25, I don't remember, 25 histories over the world. And to confirm our hypothesis, it's a work performed with Mario Ricciotto and Andrea Filippini at INRIA. We computed about more than 200 cases, numerical cases, in convergent estuaries, and we explore the parameter space, and we found nearly the same trend, and a critical curve, epsilon c, above which, for each point, there is one estuary configuration. And so if you are interested in a specific convergent estuary in your country, you can compute the characteristic epsilon 0 value and phi 0 value. And so it is, if it is located here, there is no tidal bore, and here in red, tidal bore. So we have a global classification of estuary to know if tidal bores occur or not.
It is exactly the same epsilon c function?
No, you can see that it starts close to 0.3 and here 0.2. The main difference is that in this simulation, in fact, in alluvial estuary, shallow estuary are generally you can see shallow alluvial estuary, which are most of the time convergent, with the section R is decreasing upward. And so it seems very complex with meander, it looks like very complex. But in fact, if you compute the section B of the estuary, and if you plot, B is in green, and you plot the section in function of the along channel coordinate, you can see that there is a decrease, an exponential decrease. So, and it is the same for many other alluvial estuary, convergent alluvial. And in fact, this law is related to a morphodynamic equilibrium. In fact, when you have strong tide and alluvial estuary with sediment, there is an interaction between the flow and the morphology, which lead to this funnel-shaped estuary. So it is a universal law, in fact, a morphodynamical law. And so we can consider that the schematic representation is an exponential decrease of the section of the channel. And most of the time, the water depth is nearly constant. So, with our simulation, we... Non, j'ai loupé. We use a flat bottom. And it is not exactly the case in the field. Generally, the classical bathymetry, so you have the convergent estuary. And the bathymetry here is like that. So nearly the water depth D is nearly constant. And in the upper part of the estuary, the water depth is decreasing. So in the field, it is like that. So the decrease of water depth is favorable to bore formation. So bore occurs for smaller epsilon value. And in our modeling approach, we neglect the decrease of water depth in the upper part of the estuary. So, and there are also other approximations, many other. Other questions? No? So it's time to conclude with a few open questions. There are many, many open questions in this field, of course. Just two. The first one is related to a mechanism related to vorticity, mechanism of vorticity generation by breaking the macro vortices and so on, which play a very important role in sediment transport and so on. So I presented a modeling of the generation of vertical vorticity due to wave breaking with a very simple shock wave approach following this expression. So we were able to qualitatively describe rip current circulation and macro vorticity, but vertical vorticity, so for horizontal vortices. And Richard and Graviluk in 2013 developed a modeling of the generation of horizontal vorticity at a smaller scale. It is a very important contribution due to wave breaking. And Castro and Lan in 2014 derived a 2D fully nonlinear long wave model in the presence of horizontal vorticity. So they were able to represent the interaction between vertically shared mean currents and nonlinear dispersive wave. But we need, in fact, a general formulation including all these processes. So it is really an open question. And the last one is a question about more technical, but very important for oceanographers like me, related to bathymetry inversion. So in the field, it's very, very difficult to measure the evolution of the bathymetry because it is a very energetic environment, and bathymetric surveys are very, very difficult to perform. And so at present, we use video system from fixed video system or with drone, and we compute the wavelength, the period of the wave, and we have a very simple approach using the celerity equation. We can inverse the problem and found the water depth, so the position of the bathymetry, but with errors of about 10 or 20%. So it's not accurate at all. But recently, LiDAR system has been developed and deployed in many environments. And this, you can see a scanner LiDAR, which scans the surface elevation, like this. And this technique is very accurate with a very high spatial and temporal resolution for the surface elevation. And it will be very nice to be able to inverse, I don't know, the Sergin-Naldi equation, or perhaps even the Euler equation, knowing the function zeta xt, to inverse this function to get an accurate representation of the water depth. And if it is possible, it would be very nice to observe the long-term evolution of the bathymetry. Okay, thank you for your attention.
Thank you.
Questions, remarks? Ouais.
So, thank you. Just a technical question concerning the movie show of submersion on a city, in an idealized city. It seems to me that the buildings are represented as numerically like a very steep topography.
Yes.
Is it okay?
Yes.
So that means that your shallow water part in your code is able to handle discontinuous topography or very steep gradients of the topography.
Exactly.
Okay.
Exactly. With a well-balanced scheme.
Right. So it's you did not encounter problem at that level. It's just
no, it's relatively stable.
yeah.
Yes.
Okay.
Yes.
So just thank you.
Actually, I had a question on that, and on, both on this video and on the BRGM Marche video. So it's exactly the same model running in the town and in the ocean, right? It's you're not coupling two different models, and it's really the same shallow water and Coinagdi.
No, in fact, in this specific case, the offshore wave condition is given by spectral model, spectral
okay.
wave model.
Okay.
I think it was the SWAN model.
Okay.
And the boundary condition of the shallow water model is given by the result of this spectral model.
Okay.
So so the simulation is not a whole Grignaldi simulation.
But on the urban versus ocean frontier interface, you don't have any coupling. That's the question of Arnaud. You continue to run the shallow water model inside the city.
Exactly. It is the same system of equation.
Okay.
And for that, we need a very accurate representation of the topography, of the building, at a very small scale. And in fact, BRGM used LiDAR measurements. Mm-hmm. So the accuracy, I think it's about 10 centimeters, so it's really accurate. You can see cars parking.
Yeah. Okay. Okay, thank you. Other questions? Okay, so as you understood, there are PhD and master students opportunities at Epoch with the swimming classes included. So thank you, Philippe, again for these talks.